Infiniband in the context of the future DoE systems, and in a broader context in terms of future directions towards extreme scale size systems. So, sort of to put in context the directions that we're trying to take, it's sort of important, or is more than sort of, it's very important to understand what goals we're trying to achieve in the long term, so that we can incrementally address the issues that need to be addressed towards reaching these goals. And so what I have here is a slide. I'll talk here in a moment about the real challenges that we need to address in this context. As I alluded to before, I think by this stage it's well known that Infiniband is a network that was selected in providing the two of the coral systems for DOE. The one that's scheduled at Oak Ridge called Summit, and the one scheduled to be delivered to Lawrence Livermore National Laboratory called Sierra. Really, the goal of these systems is to provide improved application performance. Their stated goal is a factor of 5 to 10 larger than current systems. And along with IBM and NVIDIA, we're primary providers of this solution. Our solution, the piece of the solution that in terms of network performance and network characteristics, is our EDR technology. I'll talk about it in a bit and give more an idea of what sort of characteristics we're bringing to the table here. So, getting back to the sort of goals that need to be addressed here. These are challenges that came up in several studies. By this stage, these studies are fairly dated. They're 5 years old or older, but not much has changed in terms of what people think. Well, actually, some has changed in terms of what people think these large-scale systems may look like. So what I have listed here on your left-hand side are the challenges that I pulled out of some of these studies, and really what the impact this has on the network. You know, what sort of network characteristics do you need to have to help and address these issues? In green, I've highlighted the particular aspects of this that I'll be talking about today. So I'll go briefly over this. So first of all, functional unit count is expected to be very large. So the numbers that have been tossed around are on the order of 10 million functional units. You know, what does that mean? This is really, I'm sorry, this is to achieve exascale class computing. What does a functional unit mean? That's a big question. I mean, there are a lot of churn going on now in the industry. Is it something like a GPU where each unit has several thousand potentially very small processors, or is it something more multi-core? The range of what this may involve is fairly large, but there are several impacts, direct impacts on a network that needs to support such a system. So first of all, the obvious is that it needs to be scalable. If you're going to try and communicate potentially with a large number of endpoints, whether it's 10 million, whether it's 1 million, 100,000, whatever that is, it's a very large number. So you have to have some sort of scalable infrastructure to deal with this, both in terms of performance and in terms of the resources required to achieve the performance. The other thing that comes into play on the network level is you have to be able to adapt to congestion in the network, and adaptive routing there becomes very, very important. In terms of on-node functional unit count, at the time the projections were on the order of 500 or so, potentially. I think that number may be somewhat small, given what we're seeing these days. Trend to go for much larger, much beefier single nodes. If you think, for example, of the DoE systems that are expected to deliver somewhere on the order of 15%, 20% of a peak exascale system, you're talking about systems that are on the order of several thousand nodes. And so they're the number, and where each of them has not only very powerful CPUs, but also several GPUs. And so that functional node count may be even larger than that functional unit count may be even larger. 500 may be quite a low estimate here. The main challenge this poses to a network is in terms of a single host channel adapter or a single network endpoint. It needs to be able to deal with a lot of sources and destinations of data. So it has to be very, very scalable. Deeper memory hierarchies need to be able to deal with networks that are cache aware. Again, the issue of resource footprint per functional unit is a very big deal. And so they're really the need to be able to do low latency, high bandwidth computation very, very rapidly is important. A functional unit heterogeneity looks like it will be maybe in play here, and so need to be able to deal with this at the network level and not require the apps to, every time they try and do something with data, understand the who's processing the data and where it's destined to or where it's coming from. Failure is a normal part of operation, and so there needs to be resiliency through the stack, both in software and hardware. Data movement is expensive and is very energy. On the energy side of things is very expensive, and so need to be able to do things to optimize the data movement. Independent remote progress is important, especially if some of the predictions come true, that you'll be able to really take advantage of these sort of very large systems. Need to be able to compute very small amounts of do very small amounts of computation rapidly, taking some sort of remote input. So really need to be able to have independent hardware progress to progress these very quickly. And of course, power costs are in everyone's mind. So so our approach at Mellanox to really providing these sort of solutions all revolve around providing a standardized solution, both at the interconnect level as well as the software level, and actually work on changing the standard over time to meet the requirements that come forward from these high performance computing requirements. From a technology perspective, we've been evolving our network capabilities on a very regular basis over time, starting on the order of 15 years ago. We've just entered the realm of our ADR technology, which is what I want to talk about today. So that part of what I'll talk about today. And so, from a technology perspective, the EDR has three components to it. It has a host channel adapter. So first of all, the technology itself is 100 gigabit per second technology for single stream. And so, from a technology perspective, ConnectX-4 is the relevant adapter for this. Switch IB is the switch, the EDR switch that's in use. And in terms of cables that are necessary to finish the hardware ecosystem, we have both copper, optical cable, as well as silicon photonics for this solution. I'll talk about these in a bit more detail now. So first of all, switch IB This was demoed at Supercomputing, introduced actually at ISC, if I remember correctly. This switch is a 36-port device, able to drive 100 gigabit per second bidirectional through all the ports simultaneously. The latency to go through this switch is 90 nanoseconds, so it's down from the about 200 that exists on FDR today, so a significant reduction in latency there. As I mentioned before, the throughput is really 100 gigabit per second bidirectional. It has some interesting features that are added and enhanced to it and enhanced in it. One, we've added in-hardware support for an Infiniband router, which means you can now start using Infiniband subnets within your compute environment, and use RDMA to send data between the subnets. So if you want, you can isolate your compute network administratively from your storage network, both using Infiniband, and you can still use RDMA to put data directly where it needs to be, rather than having to use some sort of send-receive protocol that usually involves some memory copies. Adaptive routing has been supported in our hardware for quite a few years. We haven't really exploited it a lot, although we have opened it recently and seen some very, very nice performance improvements when as the system grows and congestion becomes more of an issue. In Switch IB, we've added an additional capability that we call adaptive routing notification, which I'll talk about here briefly, to help accelerate convergence of adaptive routing. ConnectX-4, this is our HCA adapter that's scheduled to start shipping this quarter, I should say, within the next couple of months. It's a VPI device, so supports both InfiniBand and Ethernet. Runs at 100 gigabit per second bidirectional, and is backward compatible with previous rates. In terms of Ethernet, it also Ethernet can run the speeds you see listed here. In terms of some of the sort of very, very basic speeds and feeds, as I said, it's a 100 gigabit per second adapter. Latency, this is latency measured at the verbs level with a ping pong test. Verbs ping pong test under 0.7 microseconds. The message rate is 150 million messages per second. This is slightly up from what we have in Connect IB today, basically because the card is running a bit faster than the Connect IB card was. In terms of a few more of the characteristics of this card, so we've added hardware support for integration with the Power PC, so that there's hardware support for the CAPI cache coherency protocol. So the card and the CPUs are coherent at the hardware level. We continue to support the Core Direct technology, and they've actually made some improvements to it. So for those of you that are not familiar with the Core Direct technology, this is technology that was added probably on the order of 5 years ago or so to basically make it possible to have traffic in one flow or one queue pair be metered by events coming from another queue pair. Basically, it gives you the ability to build dependencies in data traffic, and is very, very suitable, for example, for collective communication that's used, for example, in MPI or SHMEM or the like. I actually have slides on this further on in the talk. We continue to support GPU Direct RDMA. This is something that we've been working on with NVIDIA for several years. We're in generation 3 of this and are progressing towards generation 4 of this technology. Dynamically connected transport, which I'll talk about here in a few slides, is our current scalability answer, our current answer to the scalability issue. Provides the ability to scale up to very large clusters with resource requirements that are independent of the size of the system. I'll explain briefly in a while why this is the case. And we also have added support for Ethernet offloads. So as I said, this device is scheduled to ship this quarter. It's working right now, and so. So really, one of the focuses of what we do is really try and make sure that we provide leading edge capabilities. Some of the capabilities here have to do with latency and bandwidth. These are some data that comes from DK Panda's group at Ohio State, where these are bandwidths that were measured on Connect IB, not on Connect X4. So we see the basic message here is the technology that Connect X4 is based on. It's the same technology used, the new technology used for Connect IB is very scalable, able to get very high percentage of peak, and able to get good latency. From the standards, so hardware is one aspect of the solution. And as I said there, we continue to support the open Infiniband standard. We'll continue to do that. We'll also on a regular basis are enhancing the standard to bring in capabilities that are really necessary to address some of the issues at scale. And these are some of the things that actually were very attractive in the context of the Coral bid, for example. We're adding some capabilities that we're not going to talk about today, but adding some capabilities that really make the network very suitable for large scale. The other things we focus on too, of course, is on the software side of things. We do put quite a bit of effort into software, both middleware, which evolves. The verbs middleware is evolving now towards lower overheads and the like, and as well as MPI and SHMEM. We also put quite a bit of effort there into providing solutions that are usable. So we really do work to provide an end-to-end solution for those that want to use our network. So let me start switching from sort of a very high-level description of the characteristics of our EDR technology. It seems to be very relevant now since it's becoming available, is becoming available. Let me focus more now on the technology side of things and some of the actual characteristics of our technology that make it suitable for scaling up to large scale systems. And let me first talk about dynamically connected transport. So dynamically connected transport was introduced first in Connect IB, our second generation FDR product. The goal of dynamically connected transport is to address the issue that everyone trying to run networks at large scale faces, is how do you build a network that's efficient, but at the same time has a resource footprint that's reasonable, that doesn't grow with the size of the system, or doesn't grow at least linearly with the size of the system. In our case, it's fixed, and provides the sort of performance one needs out of this. So in Connect IB was the first implementation of this transport trying to address this issue. And let me check here. Let me stick here. So briefly to describe this transport, It has some of the characteristics of unreliable datagram in the sense that you can have, or any unreliable datagram or some sort of connectionless protocol, where you, from a given endpoint, you can send data to any other endpoint in the system. So you're not, you don't have to create resources that grow quadratically based on the number of communicating endpoints that you have, whether it's a full system or whether it's a partial system. The other characteristic that it has is it supports RDMA protocols. So it supports RDMA read, RDMA write, atomic operations, which you can't use with UD. So you can really make remote progress without involvement of the remote CPU, which is very important to us. And the other thing that it provides too is it's a reliable protocol. And so you don't need to add reliability in software. Now, so one of the attributes or one of the challenges that we get in using this sort of protocol is that we need some sort of mechanism to deal with reliability. We need some sort of long enough term context to know what to do when data is lost or when data is corrupt, not just drop it like one might do with UD, for example. And so this requirement is what leads to the design of this algorithm. So briefly, this algorithm this protocol is a unidirectional protocol. So you have initiators and you have targets, and you send from initiator to a target. The initiator has to live long enough to support the reliability protocol. So you can't just fire and forget like you can with UD, for example. You have to have context long enough to be able to do something if you have issues with to guarantee reliable delivery. And what this means from a practical perspective is really when you're sending data to a target, as long as you're sending data to the same target, you can continue sending from the same QP with no delays. But at the moment you want to use that initiator to send data to another target, the initiator first has to complete the traffic that's sent to the current target before it can start sending data to a subsequent target. And what that means is there's a latency delay. And so to deal with that latency delay, you need to use more than one initiator. So to basically hide that latency. So the scalable aspect of this comes from the observation. Actually, let me step back. I should say so. Worst case scenarios where you're trying to send a lot of small data, and your round trip latency is 2 microseconds. So you really have 2 microseconds between the minimum of 2 microseconds between sending data to different targets. So that's a challenge that needs to be overcome. And so if you think of the fact that a given host can send data there's an upper speed that a given host can send data that depends on the characteristics of the CPU that prepares the communication, as well as the characteristics of the network. So let's take the case of ConnectX-4 so we can use round numbers. In ConnectX-4, a single device can't send data faster than 150 packets per microsecond. Okay, so what you really need, if you're going to try and cover a 2 microsecond latency, what you really need is enough initiators to cover that 2 microsecond latency delay. So if you take the 2 microseconds, the fact that you can send 150 packets per microsecond, 300 initiators saturates the network, independent of the size of the system. Say independent, it's not 100% independent because as the systems grow larger, if the number of hops grow larger, it grows slightly more. But it's a very, very weak dependency on the system. So the number of network resources you need to keep the network busy at all time, if that's the only thing you're doing, is on the order of several hundred initiators to do that, and that's well within the limits of what single card can support in its caches, and so a very good protocol for scalability as well as performance. Cartoon here, it's more than a cartoon here, a slide here on the amount of resources used as a function of protocols that are used, evolving over time, starting back in early 2000s with initial reliable connected transport. So we've drawn here the amount of memory consumed in megabytes as a function of system size, and as everyone knows, that really grows quadratically because of the nature of RC. Using shared receive queues helped because it reduced the amount of buffers that one had to set aside for the receive side. XRC was a way to share even more resources and reduce the memory footprint, but dynamically connected transport is really really gives you essentially a constant memory footprint, which is what you want, and the performance and the ability to really make independent progress, remote independent progress, which is very important on the app side of things. So I don't know if this animation will work. Sometimes it does, sometimes it doesn't. So from a conceptual perspective, I've drawn here. Actually, someone drew for me what connections might look for a cluster that uses RC, reliable connected transport. Because very dense connections, static within time. But the nice thing about dynamically connected transport, it's going to work. Well, this is supposed to animate and change over time, because what happens in dynamically connected transport, the user is not at all involved in determining what connections are set up, how long these temporary connections are set up for. This is entirely driven by the hardware and entirely driven by actual data that's posted to the network. So as time changes, the connections change based on application use of the network. So let me talk a bit about topologies here. The next thing, because this is an area that's very important from a scalability perspective. Very important from a scalability perspective, and an area that we're constantly doing work in. So today we actually support 4 topologies. 3 of them directly, through our software. The 4th one through open source software. A few things to say here. First of all, our network is really topology agnostic. There's nothing in our switches that is designed for one topology or the other. Everything, what happens in communication. Communication is table driven. You have tables that tell you how to forward data over time. And those tables are configured based on the topology that the system is set up with. So the subnet manager configures those topologies. Today, as I said, we support and have supported fat tree for a long time. It's a topology that's well understood, has very nice scalability characteristics, very predictable. We also support Tori, 3D Tori. We have several of those out in production. Those systems have people that use those tend to want. This tends to give a lower cost type of solution, but also less global communication capabilities. There's less global network provisioning, and so they're really. If you have applications that are very whose communication pattern is very local, So this is a good network, a good topology to use. We've also added support for Dragonfly type topologies. So for those of you that are familiar, for example, with a Cray network, our topology is slightly different for several reasons. So the Cray network, each of the subgroups. So first of all, let me step back. A Dragonfly topology is generally is one way to describe it is a bunch of local groups all interconnected in an all-to-all type fashion. The Cray's version of topology, they use a 2D flattened butterfly. So that's what that is essentially is a 2D mesh, but in each direction, everyone is connected in an all-to-all manner. So you have a 2D type of local topology. We've chosen to base our support on a two-level fat tree for several reasons. One, in terms of network hops, it gives us less router hops through the network if we use the fat tree versus a mesh, versus the flattened butterfly. The second reason, because the basically the topology of the two-level fat tree is very, very directional. You just have either up or down, no other directions in your network. What this makes it possible for us to do is use only 2 levels of quality of service to avoid deadlock in routing. So in a network, in our switches, for example, where we have 8 virtual lanes, this lets us still provide four levels of quality of service with the switches while using this topology. Versus the one that's based on a 2D Dragonfly, 2D flattened butterfly takes at least 4 levels of 4 virtual lanes to be able to have credit-free routing to avoid a deadlock in routing. As I said, we continue to work in this area. We continue to look at topologies that may be more suitable. We continue to evaluate that. We have customers coming with us asking us about topologies as an area that's important. It determines a tremendous amount about in terms of overall network performance as well as cost. I should say when it also adaptive routing that we've added in terms of performance, adaptive routing helps as well as resilience helps in all of these topologies. Even though, as I said, everything, all of our routing, even our adaptive routing, is based on some sort of default set of routes. The adaptive routing capability lets us, in cases of congestion, take alternative routes, and get better network performance. And we've actually seen some very nice improvement in network utilization within the last couple of months when we've looked at these sort of things. And the other thing that it lets you do is when you have failure, it lets you route around this failure and continue without having the application fail. So a bit more about adaptive routing. So there's really 2 purposes in terms of adding support for adaptive routing. One, to improve overall network utilization. So really the goal here is to deal with congestion. And that, of course, is most relevant for larger data transfers, although it is obviously relevant also for small data transfers by being able to take advantage of more of the network resources that are available. The other thing that it's very helpful with, as I just said, is dealing with failure. So when a link goes down, be it temporary or be it permanent, the hardware immediately starts adjusting to these failures in parallel with the subnet manager reconfiguring new routes. So you really do continue using your old default routes and routing around the failures as the subnet manager is computing a new set of default routes. In terms of the hardware that supports this, as I mentioned before, switch X2, the previous switch, we can say now, the one that's by far used in greatest use out in the field, it supports adaptive routing. We've exposed that support recently, and as I indicated before, we've started to use that support. Switch IB, which is the EDR switch, continues support for adaptive routing and adds the new capability that's called adaptive routing notification, which I'll describe here briefly. So in terms of what's actually done with adaptive routing at the hardware level, first of all, there is not one. You can use more than a single policy. You don't have to either use adaptive routing on everything or not at all. The network is configured. The switches are configured so that you can decide which traffic you want to adapt and which traffic you will not adapt. So when a packet comes in, and you can also make decisions on a packet-by-packet basis. So when a packet comes in, the first decision that needs to be made is whether or not to use a default route or to use another an alternative route if that's a packet that can be routed, can be adaptively routed, I should say. And then if the decision is to adapt the route, is which route to take. So these are all configured by policy. These are all determined by policies that are configured into the switch. I won't go into details on how this is done now, but this is something that's configurable. There are several different options that can be used here. I mentioned before our hardware is not topology specific. It's topology agnostic, and all the rules that go into configuring the switches are based on the topology you're trying to route for. In terms of modes of adaptive routing that are supported, there are, I should actually say, there are 3 of them. One is static, where you always have a fixed port for a given destination. You always have a fixed port to use. The other is time-bound. Another is time-bound, where you have a certain period of time in which you won't adapt the flows, and you also have free adaptive routing, which can be done on a packet-by-packet basis. And so these are really these within a single run of the application. You can actually use all of these simultaneously. These are all configurable. Packets are classified. The packets themselves are either classified as legacy, which means no adaptive routing at all. Restricted, so you'll do some adaptive routing, or unrestricted. Same thing about the destination in terms of how one might select a destination. You can have fixed destinations. You can have fixed exit ports for a period of time, or you can have freedom to select basically on a packet-per-packet basis how to do this. And there are quite a few options. You do the matrix. You have about 12 different ways you can adapt packets. This is all table-driven, all very, very fast. This is not something that increases latency much. Latency, as I said, is 90 microseconds through our 90 nanoseconds through our current switch. And a bit about what adaptive routing notification is. So one of the big challenges in adaptive routing is how to properly select a new route. Ideally, you really need global knowledge, but global knowledge is too expensive and not practical, and so you need some sort of compromise to help help in terms of choosing how to adapt the packet, how to choose a new route. And so this is really what adaptive routing notification is the problem adaptive routing notification is trying to address. So when a switch detects that there's congestion, this new capability uses the ability to support switch-to-switch communication, administrative communication that happens at switch latency. So it's very, very low latency. And so when a packet comes in and detects and the switch detects congestion, at some point it'll decide that it needs to reroute the packet. And when it decides that it needs to reroute the packet, it'll send an adaptive routing notification message to the switch from which the data came from. At that point, the receiving switch looks to see if it's the source of the data. If it's not the source of the data, it forwards the data to the previous switch because it can't fix the problem. And when the notification reaches the source of the data, that switch can actually make a decision that will have positive impact on the overall flow. And at that point, it can choose a new route for the data and start using the new route. So that's basically the idea behind adaptive routing notification. The advantage that we have here is this is really integrated within the switch protocol. The latencies at which this happens are very low latencies of switch latencies, which tend to measure in tens to low in the hundreds of nanoseconds. Simulations have shown that this algorithm converges in about 10 microseconds. So very, 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 very fast. Let me switch gears and talk a bit more about offloading capabilities to the network. So one of the big directions one of the big driving forces behind new technology that we introduce to our HCAs is the desire to move as much management of communication away from the CPU as possible, to leave the CPU for computation, which is usually what apps want to use it for. And so we've been slowly working on migrating these sort of capabilities to the network. It starts even with a very basic basic functionality capabilities being the queue pairs. They all reside on the network itself. There's no once you put data to the network, there's no more CPU involved in moving data, and so over time we're increasing the capabilities, the capabilities that are supported, that are offloaded to the network. So what I'll talk about now is specifically about the technology called CoreDirect. CoreDirect is a technology that was implemented first in hardware about 5 years ago. It came about as a Department of Energy funded research effort, actually, between Mellanox and Oak Ridge when I was at Oak Ridge. And the goal of this work was to really deal with scalability of collective operations, scalability as well as the ability to support non-blocking collective operations. I have a few cartoons here that will explain briefly what the challenge is in terms of collective operations. So first of all, I should say that in scientific HPC, collective operations are typically the operations that most determine applications' scalability as well as performance at scale. Usually, as you scale up, the things that tend to bite you is the performance of collective operations. There are, of course, things on the Application side of things, if the amount of work you can do gets too small, you can't really scale. That's an issue, but that also typically manifests itself through network problems because you try to move data around, and you can't move it around fast enough. The basic challenge with a collective operation is all collective operations involve all elements of a given group participate in the operation. And so specifically, in what this translates to in many applications, it means that all processes in the job participate in a given instance of a collective operation. This is not all the way it always happens. In MPI, as many of you in the room know, you can form subcommunicators that are smaller, so you have collectives over smaller groups. But the nature of the problem remains the same. And the problem is that by their nature, there's some sort of there's always some sort of implicit dependency between processes that are participating in the collective operation. So I have a cartoon here that reflects data going to some sort of something happening, some sort of operation that involves rank 0 here. I'm using MPI terminology, being basically the bottleneck. Something has to happen at rank 0 before everyone else can finish the operation. So this communication pattern could represent the barrier. It could represent some sort of reduction, and the like. And the problem that happens is so first of all, you see that in first process 0 can't participate in the collective operation until it received data from process 1. You can see the same thing here. 2 can't participate until it got data from 3, which can't do anything, and 0 can't continue until it got the data from 2. So there's an implicit dependency here between processes. The first issue, or one of the issues that arises is on the system. You have the operating system needs to service other things, not just strictly application computation. So periodically, you have system activity, which is called system noise. And for those of you that are, and so basically what that means, it's a period of time where collective communication, where the application is not getting any quanta, any time. The kernel is, or something else is. And so because the coupling between different processes in this group, this lack of time, unless the ranks are very well synchronized, this lack of time translates into slowdown and into reduction in performance. A very well-known paper from early 2000s at Supercomputing describing the effect of system noise on the Q computer at Los Alamos at the time. It showed a factor of 2 impact on application performance at about 6,000 processes, if I remember. Don't remember the exact details. But the point is that this is has a very negative impact on application performance. If you can move the management of collective operations to the network, then once you post the collective operation to the network, you're no longer susceptible to that system noise because the management of operations happens on the network independent of what's going on in the CPU. So if the operating system wakes up and decides to handle some interrupt or something, I don't know what, it's not affected. The collective operation is not affected, on that process is not affected by that particular activity. It's not slowed down in that process by that activity. The other thing that you can do is, the other motivation for doing this offload is, if you want to go to truly non-blocking collective operations, you can basically fire and forget. You can just start the collective operations, and when you need the data, come back and check and see if the data is ready. Hopefully you have enough computation to hide that latency and not pay the cost of the collective operation. And so, this sort of capability is supported now, or has been supported for several years in MPI. Applications are starting to use it. It's still very early phases of that. The SHMEM standard, I don't know if anyone in the room here is interested in SHMEM, but those that are, the SHMEM standard itself is also considering adding this sort of support for non-blocking collectives. It's very important for scalability. Let me not go through all the details here in terms of how one sets up these operations. Just give you the gist of the flavor of what the core direct capability is. It has added basically some primitives that let you synchronize activity between independent Q pairs. So you can, on one Q pair, you can say, wait here until a different Q pair has completed its communication, and then go ahead and send the data. That's the very basic gist of it. So it gives you the primitives you need to be able to coordinate and build data-dependent communication patterns, which is what you need to support collective communications. Let me skip. So just in terms of performance, this slide shows the ability to overlap work with a collective operation. So I have on the left-hand side here the amount of overlap that one gets, overlapping work and computation. This is for an all-to-all operation. Here I have the message size. The top figure uses the core direct capability, so it does not use the CPU at all for progressing communication. The bottom line is a traditional CPU-based algorithm where you need to use the CPU periodically to progress the collective communication. This particular benchmark is trying to use as large a quanta of work as possible, which is what applications typically want. And we see that, as expected, since this is what the hardware is designed to do, there's very, very good overlap of computation and communication. So this is really what it was, one of the things that it was designed to do, and it does it well. The other feature that I'll mention very, very briefly. In ConnectIB, so as I mentioned before, really, what we're trying to do as we evolve as we progress our hardware, is to free up the CPU for computation as much as we can. And so in ConnectIB, we introduced a new feature that lets you deal with that lets the hardware deal with aspects of non-contiguous memory both at the source and destination. So previous to this capability, if you use Infiniband or if you use a lot of other networks too, if the user has non-contiguous data that they want to send, for example, let's take the simplest example where you're doing some sort of near-neighbor communication, trying to do a halo exchange, so you're exchanging, the edges or something like that. You typically have non-contiguous data there. Typically, what's done by applications is they'll copy the data into some temporary buffer, whether it's directly or through some sort of MPI accumulate operation. And on the other side, when they get the data, they will also copy it out. So you're using the CPU on both ends to move the data along. Prior to ConnectIB with standard InfiniBand, there was the ability to use what's called the scatter-gather list, which is, for those of you that are familiar with it, it's basically an IOVEC. IOVECs are very inefficient in terms of describing data. If you have data that's irregular, there's not much that you can do, but if you have regular repeat structure data, IOVECs are very, very inefficient. You have to, for every 8 bytes, for example, you have to have a pointer and a length, and so you have to transfer a long description to the hardware. You have to do, there's a lot of overhead in terms of just managing that. So what was added in ConnectIB are two things. One, the ability to still use things that are similar to SGE lists, but remove the restriction of lengths of 32, so you can send much longer lengths of messages. So if I remember correctly, you can go up to several thousand elements there. But the other very interesting thing, they're both interesting, but the thing that's really new is the ability to describe data, repeat structure data. The unique thing about this definition is now the definition is no longer connected to an SGE list, where you describe the SGE list with either the post send or the post receive, so that when you do an RDMA, for example, and you don't have a post receive on the other side, you can't deal with the non-contiguous data on the receive side. What you can do here is that the description is associated now with a memory key. So everywhere a memory key is used, you can deal with non-contiguous data. And so this gives the ability to do RDMA from non-contiguous to non-contiguous regions. And so I have a couple of data patterns that can be used. One, you can do what you could do. You can describe new memory regions that with a memory key that are non-contiguous in space, and send data in that form. So you can create and just address it as though it's virtually contiguous. The hardware deals with all the offsets necessary to jumping properly through memory locations. It knows how to do that. You can give it a base address that's very convenient to you. So if you want to, you can give this a base address of 0 and it works fine, as long as you use it consistently. The other thing that's very interesting is you can. I've described here a region that's not memory is contiguous from left to right. So this memory is non-contiguous. This memory is non-contiguous. You can interleave regions of memory. So this is a way to start sending portions, for example, of data structs without having to actually copy the data and consolidate it into a contiguous region. So this works now. We've actually tried to use it with some of our collective algorithms where you need to gather scattered data. It's a very nice very nice new feature. See, briefly, I got 2 minutes left over. So one of the other things that we're bringing into production is support for on-demand paging. That is removing the need to always register memory before it's used, but having the host channel adapter register pages as needed for addresses that may not have previously been registered to the card. So this obviates the need to register memory before you use it. Makes it much more convenient to use. In terms of currently what's supported is in the current release of OFED is the send side for UD. The plan is to have basically full support for all transports later this year, and so later this year people can start experimenting with the benefits of not having to register memory all the time. I will say that no need to say. I'm out of time, so I will stop at this stage. I'm a technical guy. I don't answer costs questions. I don't. I'm sure there's someone here that can Greg there in the back can answer. I don't deal with that issue at all. Not today. No. But as you can imagine, I mean, the system, the Coral system has NVLink in it. Yeah, that's right. Yeah. So what I'm saying is, yeah, Gilad said the right thing. I mean, the system with NVLink works. We just go through a PCI bus. There was an open RFP. I mean, bidders, there were multiple bidders. I mean, I don't know all of them. It was a competitive procurement.